All right, guys, so we are going to be going over, all right, our electrostatics test review. All right, it's going to be very, very similar to what we see on our test. Okay, so in this, we have the first couple questions that are based off of this, all right, chart right here. So this chart, all right, their attraction for electrons increases as we go up the list. So the ones that are higher up on the list are stronger. Okay, so paper, all right, is stronger than anyone else below it. So paper can take, when it rubs with silk, fur, wool, nylon, hair, acetate, glass, it's stronger. It's going to take electrons away from them, become negatively. Everybody underneath would become positively charged. Okay, but paper, if it's rubbed with anything above it or stronger than it, those guys would take electrons from the paper, and any one of those guys would be negative, and the paper would be left positive because it would be losing electrons. All right, remember, you can only gain or lose electrons, not protons. Protons don't move. Okay, so a girl pulls a wool hat off of her head, hair. Okay, so I see hair and wool. Who's higher up on the list? Wool. So wool is more stronger, right? It's stronger, more negative. So wool would become negative. The hair would be left positive. So who becomes negatively charged? Wool. Which one becomes positively charged? Her hair. Not her. Her hair. All right. Now, which would produce a stronger static charge with cotton? Silk, wool, or nylon? So how do we do this one? I'm not sure, but what do we got? We said here's cotton. All right, so we have cotton, we have wool, nylon, and silk. Okay. So, right, the list is basically the stronger you are on the way up. So, like, let me phrase it like this. Do you think you can take more electrons from someone that's weaker or someone that's stronger? So, right, if I'm pretty strong, you try and take electrons away from me, you're going to be able to take that many? No, but if it's like a little kid holding like a bunch of electrons, you'd probably be able to take more because they're not as strong, right? It's a silly analogy, but it's essentially kind of how it works. The materials, these substances, has a certain affinity to hold on to their electrons. So silk, right, the more up on this list we go, the stronger their attraction for electrons. So cotton is stronger than silk, but silk is stronger than wool, and wool is stronger than nylon. So let's just say, like, okay, you're here. Silk is 2 away. So cotton can take 2 electrons, all right? 2 electrons from silk. It's 1, 2, 3, 4. It's 4 away. So let's just say it can take 4 electrons from wool. And from cotton, all right, for nylon from cotton, 1, 2, 3, 4, 5. It could take 5 electrons away. So because there's a larger distance between cotton and nylon than the others, it can take more electrons away, and the larger the difference, the stronger the static charge. All right, so think about, like, hey, would you rather get shocked by 2 electrons or 5? Yeah, 2, right? 2 is going to be weaker. It's not going to be as strong. All right, the more electrons, the more charge you're going to have. Okay, like that little John Travolta's video, right, where he rubs his foot and he builds up the electrons. All right, the more electrons, the more zap. So because of that, the stronger static charge will be produced with nylon. Okay. So, all right, we're still using this chart, but let's see. They want to know what the charge of the underlined object is going to be. What's the charge of the underlined object? Okay, so let's yeet these out. Acetate rubbed with wool. Acetate's down here. Wool is here. Who's stronger? Wool, so wool would become negative, but they want the charge on acetate. So acetate would be positive. Glass with cotton. Glass is way down at the bottom. Cotton's up here, so yeah. Glass is going to be positive. It's much weaker. PVC versus paper. PVC is higher up on the list. It's stronger. It's going to take the electrons from paper, and if it takes the electrons, it's going to become negative. All right, this was back from our notes. All right, this was back from our notes. The static electric charges are charges that are stationary charges. All right, just memorize that one. The electroscope which was like this little thingy MacGyver, all right, that had the two little foil leaves at the bottom, and if it detects static charge, okay, we give it static charge, either the thing would polarize itself and the leaves would spread out, all right, or if you touched it via conduction or induction and we gave it a charge, right, if this was negatively charged and so were the leaves at the bottom, the negative and negative repel, so the leaves would go from hanging straight down to spread it out, so it's going to detect static charge. All right, what kind of charging, all right, results from direct contact between two objects? Contact, think conduction. Bam, bam. Very good. Electric forces between charges are strongest when the charges are close together, further apart, or is the electric force constant everywhere? So think back to Coulomb's law, the demonstration, all right, the little video, the simulation that you guys did. And also here is another thing. You can kind of think about it like magnets. Are magnets stronger when they're closer together or further apart? Closer together. It's similar like that with electric charge. Same thing with gravity, right? Gravitational forces are stronger when these things are closer together. Ba-bam. Boom. All right. So let's flip-a-delphia onto the next one. Coulomb's law states that the force between any two charges depends on, well, here's Coulomb's law. K is a constant, right? Q1 and Q2, those are the charges. D is the distance between their centers squared. So directly on the magnitude of the charges, well, yeah, the stronger the charges, the stronger the force. The weaker the charges, the weaker the force. Yeah, that's a direct relationship. All right. Inversely on the square, well, is it being divided by the distance squared? Yeah. So if we increase the distance of separation, right, you're not just doubling the distance between them, you're doubling it squared. So it's 4 times as weak. So you're dividing it by a larger number. When you divide something by a large number, okay, the result is going to be weaker. So it's A and B, which would be both. 12. Two charged objects have a repulsive force of 0.08 newtons. So this is like from the other assignment that we did a couple classes ago. Okay, that was the Coulomb's law, all right, assignment where we had to go through, and if they change, all right, if they double, right, this is the charge of the first object, charge of the second object, distance between them squared. We don't put the K in here because that's a constant that never changes. And then we just kind of play around with the numbers, right? If the charge on one of them doubled, we'd make one of the charges a 2 instead of anything else. And the other charge didn't change, so we leave it a 1. Distance didn't change, we leave it a 1. You have to square it, play it out. It becomes 2. 2 times the original force. If that's the original force, you multiply it. If you double both of them, all right, both charges become a 2. Play it out, all right, and work it out. Distances, if you double the distance but not the charges stay 1s, the distance becomes a 2, you have to square it, it's 1/4, etc. Okay, so it's a combination of that. So in this one, if the charge of one object is doubled and the distance is doubled, so what do? Okay, so the charge on one of them doubles, so one of these is going to become a 2. They didn't say anything about the second charge, but then they said the distance is also doubled. We have to make D, the 1 on bottom, turn that 1 into a 2, but you have to square. And let's play that out. What's 2 times 1? 2. 2 squared, 4. 2/4 reduces down to 1/2 of the force. So then you just, for F, you put in this number. So you're going to do 1/2 of 0.08, and that is going to give us 0.04 newtons. C. All right, and then they kind of do it again in 12. All right, that was 12. I'm sorry, 13. When the distance between two charges is doubled, what happens? Distance is doubled. Okay, they didn't tell me anything about the charges, so they both stay 1s. All right, charges stay 1s. Distance is doubled. You've got to square it still. 1 times 1 is 1. 2 squared is 4. 1/4 of the force. All right, we do 1/4 of that. Oh, we didn't even need to do that. It's literally just going to be the 1/4. Aha. So we didn't even need to multiply it by that 0.08, so we are good. Answer would be C, 1/4. 14, if the distance between two objects doubles, but the magnitude of each charge is increased by a factor of 4. Okay, wait a minute. Distance doubles. So D goes on where? The bottom. So the bottom one doubles, we got to square it. And then it says the magnitude, which is the size, right? So each charge increases by a factor of 4. So instead of this being a 1 and 1, they both are going to become a 4. Okay, so 4 times 4 is 16. 2 squared is 4. And if we divide this out, 16 divided by 4 reduces down to 4. 4 times the force, so our answer here would be 4. All right, that's our little guys proportionality type problems with Coulomb's law. Now, which subatomic particle carries a negative charge? This one should be super easy.
Electron.
Yes, the electron. Okay, a neutral object. Can a neutral object ever be repelled? Absolutely not. So A is definitely not an option. Is a neutral object attracted to a positive charge? Yeah. But it's also attracted to negative charge, not just one or the other. So it can be attracted to either a positive or negative charged object. So we have the letter D. What happens, right? So remember, all right, if you don't remember, like, you may want to just briefly add this to your thing, right? A negative and negative, what are they going to do? All right. They good. They repel. And what other ones repel? Positive and positive. Okay. Those ones repel. The ones that attract, negative and positive. They attract, negative and neutral, and positive and neutral. All right, that may help you guys answer quite a few questions on here, at least two extra ones. All right, what happens when a positively charged rod is brought near a neutral metal ball? Oh man, you're like, how do I figure that one out? I'm telling you right now, guys, this would be the easiest thing for you to do on the test would be to draw it out. What type of rod? Positive. So you just draw like a little rectangle and give it a lot of positive charge. Brought near a neutral ball. All right, so let's just say it's got 4 protons and 4 electrons. It's close to, but not there. We said, right, that opposites attract. So the electrons in here are attracted to the positive charge. So the electrons are going to want to move to which side? Left side or right side? So that would mean they would all kind of go over to this side, which would mean they're being repelled by positive charge. But we just kind of said that opposites attract.
Oh, yeah,
right? So the electrons would scooch over to this way. So if I like redrew this out right quick. All right. This side of the sphere would become negatively charged, which would leave this side more positively charged. So what they're asking, how do the electrons move? Well, here's a quick thing. The protons are attracted, protons are repelled. Well, they're not really moving around, all right? It says like, oh, the protons move and move. Protons don't move, so it eliminates right there, right off the rip, options A and B. You can't have them. So which one closely resembles this picture? Electrons are repelled to the far side, or, all right, to the near side. And this should be not plastic ball, because on a plastic ball it's not going to happen. All right, electrons in the ball are attracted to the near side. All right, to the near side. So we are looking at letter D. An electric charge that results from the presence of a charged object nearby but no direct contact. So it's like this, okay? Results from the, all right, we basically kind of polarize this thing. This one we're going to have as induction, all right? Induction, without making direct contact. Obviously, it's not friction, okay? We haven't talked about a proximal charge. We're looking at B, right? We already know All right, yeah, so we're looking at this one here. Let's go to the next one. So, oh no, again, I have to make a correction on this one. That was my fault. So in 19, it's going to look like this. Add this one here. All right, you're going to have on your test, this picture will be there. I'm so sorry that I forgot to correct this. You're going to have two negatively charged rods like this and a positive charge here in the center. So they're going to ask, how is the positive charge going to move? Is it A, going to move in this direction? Is it B, going to move straight down? C, is it going to move straight up? Or D, down and in? So how would the positive charge move? A or B? Well, is positive attracted to negative? Yeah. So if that's the case, if positive is attracted to negative, all right, this thing would be attracted down this way and this way. So which way do you think it would actually move? Kind of in the middle, right? So it would be like a little bit to the left, but also down, which would kind of put it right here in the center. So we'd be looking at letter D. We'd be looking at letter D for this, okay? So make sure you draw that in. All right, and then 19 would be D. That one, again, you will have on your test as well. So similarly here in 20 through 23, you're going to want to just kind of add a little bit of a picture thing in here. All right, a negatively charged rod is brought near but not touching the right side of a sphere. So I just kind of draw a sphere. It's on the right side and this thing is negatively charged. So what are the electrons going to want to do? Electrons, are they going to want to go towards other electrons or be repelled? Opposite, right? Same charge is repelled. So the electrons would want to go to this side, which would leave the right side positively charged. So this one would be like letter B. Now a positively charged rod is brought near but does not touch the right side of a neutral sphere again. So now the rod this time is positive. And now the electrons in here are attracted to this, so the electrons kind of go to this side. They line up over here, leaving the opposite side more positively charged. What picture looks most like that? A. Okay, a negatively charged rod, negative charge, touches neutral, it becomes, all right, that's conduction. All right, and when you touch two objects, a charged object touches a neutral object, okay, through conduction, they are going to have the same charge. So it would become negatively charged, and because of that, you will have negative, which would be letter D, not just negative. Okay, this one's a little tricky. Rubber rod becomes negatively charged after rubbing it with fur. The fur is then taken and touches a neutral sphere. So the rod touches this fur. They rub together. The rod becomes negatively charged because it takes electrons away from the fur. If it takes electrons away from the fur, what's going to be the charge on the fur? It's going to be left positively charged. Okay, and then if the fur, which is positively charged, touches the neutral sphere, okay, what happens is it's going to wind up getting the same charge. Conduction is going to give the same charge. So the positive object touches this. What happens? Why? Because the electrons are attracted to this. Some of them jump over, and when you lose some electrons, okay, from here, then it's going to be left overall positively charged, which would look like letter C. Then we have the balloons. We know that B is negative. What can A be? Well, we kind of said it before. All right, what attracts negative charge? Positive, and what else? Neutral. So it's not just positive. All right, it's definitely not negative because they would repel, and it would be, if B is negative, either positive or neutral will attract this. Okay, so positive or neutral. So we got to make sure we write that correctly. Neutral or positive. So C. We already know that B is negative, and all right, neutrals never repel, and opposites attract. So this can't be neutral or positive. The only thing it could be is negative. D. Okay, so the balloon is negatively charged. So the electrons in these soda cans are going to want to be repelled. So they're going to kind of go to this side, making this side negative, this side positive. All right, so the left is going to be positively charged. The right side will be negatively charged. And that would be letter A. Okay, this one is kind of simple. It may take you a quick second. All right, there are 10 positive or negatives on each one of them, so you can count. All right, if there's more than 5 pluses, it's positive. If there's more than 5 negatives, it's going to be negative. Okay, so 1, 2, 3, 4, 5, 6. All right, so this is positive. 1, 2, 3, 4, 5, 6. This is also positive. Positive and positive will repel. 1, 2, 3, 4, 5. So it's 5 and 5. So this one's neutral. 1, 2, 3, 4, 5. 5 negatives, 5 positive. This one's neutral. 2 neutrals will do
nothing.
It's correct. Now we got a 1, 2, 3, 4, 5, 6 positive. And this one is definitely negative. Opposites do what?
Opposites attract.
All right, so they attract positive, positive, positives. So this one's all positives. And 1, 2, 3, 4. This one's neutral. Positive and neutral, what are they going to do?
Positive and neutral.
Yes, they attract. 1, 2, 3, 4, 5. So this one's neutral. Definitely, this one's more negative. Negative and neutral.
Thank you, Ina.
Okay, they attract as well. And this one is definitely negative, and this one's negative as well. 2 negatives, what are they going to do? Repel. Okay, in this one, guys, you literally have your 2 charges. Charge of the first, charge of the second, and then the distance apart. K is over here, 9 times 10 to the 9th. So you will literally just do 9 times 10 to the 9th times the first charge, 5 times 10 to the negative 8, and 1 times 10 to the negative 7th. And then you will divide it by the distance apart squared. When you throw that into your calculator, you're going to get a value of 0.1234518, and the unit will be newtons. Okay, so you need to make sure that you have the work shown and the correct answer with the correct unit. The unit will be newton because it's force. Charge of the first, charge of the second, distance. Again, K goes first in the equation, which is your 9 times 10 to the 9th, times 1.5 times 10 to the negative 6, times 3.2 times 10 to the negative 4th, divided by the distance between their centers squared, and this will come out to give us a value of 1.92 newtons. All right. So if you missed this, you guys can come back to the video and copy them in, okay? I just want to make sure we get through all of this. So this one was just like our assignment from the other day. All right, you need to remember that the electric field lines, all right, radiate out of a positive charge and end on a negative charge. So radiating outward is positive, going inward, negative. What is C going to be? Correct. D.
Negative.
Good. E and F. Good. So E would be negative, F would be positive. And G, H, and I,
They're all positive.
they are all positive. Are you positive?
Yep.
All right. Love to hear it. All right. And then this one, they just want you to rank them based on their strengths. So the stronger the charge, okay, the more electric field lines that are going to be radiating out of it. So who is going to be stronger, A or B?
A.
Yeah, so the stronger one is going to go to the right side, the weaker one to the left. Who's stronger, C or D? It doesn't matter who's positive or negative, just who's stronger, who has more lines.
D has more lines, so it's stronger.
D is more and C is weaker. Good. All right, in this one, who has the most lines?
F, the second is E, and the third is G.
Yeah, G is the weakest, and E is here. My name is Jeff. Who's the strongest one out of these? Aye, Captain. Who's the next?
E.
H is the middle,
Oh.
and J would be the weakest. Okay, got it. Okay, and then this one, it's a little bit trickier to see, but which of the following is correct between the two charges? So on this, all right, between two negative charges. So all of these little charges are negative. Which one would be correct? What do two negative charges do to each other? Repel. So which one shows the best repelling?
C.
Okay, so I heard A, I heard B, I heard C. A would probably work if this was shifted here, it would be a little bit better. But because of the angle of where they are, it would be C. Okay, and these are two positive charges. So two positive charges also do what? Repel, which means which would be the best option?
C.
Yeah. All right, and then the last two. A positively charged rod is brought close to one end of a neutral metallic plate. Okay, what type of charge is induced on this plate, all right, of the closest side of the plate? So right now, this thing is neutral. So there's even amounts of protons and electrons. How are the electrons going to want to move? How is the negative charge on this going to want to move? Towards positive, attracted to it, or is it repelled by positive? Negative charge. Negative charge is
Positive and negative attract.
correct. So the electrons are going to want to try and go to that. So they're going to try and go to this side, which would mean this side of the plate would be negative charge, and this side over here would be more positively charged. Okay, so you would basically add that drawing in there. On the test, I think it will be some form of a multiple choice. And then on this one, this last one, okay, positive rod is here. Remember, when you ground something, okay, for induction, electrons can go in or out. So the easiest way to think about it is electrons are attracted to this positive charge. So more electrons are going to come in and enter, okay, and kind of line up on this side, leaving this side more positively charged. And when you stop touching when you stop grounding it, those added electrons will make this thing more negative.
Test on Monday.
See ya. Have a good week.
Have a great weekend. Make smart choices.